Want to start it? Want to start now? Yeah. Okay. So. All right. So welcome to the seminar, and I would like to give an introduction to Professor Tharm Ratnarajah. So he recently joined the Department of Electrical and Computer Engineering at the chair professor, Fred Harris, endowed chair professor. So Fred Harris was a famous professor at our department, and he's one of the most famous professors at SDSU in Thailand, right? Well known around the world. And then when he's retired, his former students make the endowment $3.5 million and create a chair under his name. And it took us 2 years to recruit a famous renowned professor from UK, and Professor Tharm Ratnarajah joined us last September, and from University of Edinburgh in Scotland. So I think that's enough. Right.
Okay, thank you, dear. Okay, welcome to my talk. Rahman, everyone. The title of my talk is Federated Learning in Massive MIMO Network, Convergence Analysis and Communication Efficient Design. Okay. This is the overview of my talk. I will start by introducing federated learning and the system model, and then I'll talk about convergence analysis and communication efficient design. Then I will talk about extensive simulation results. Then finally, I'll give my concluding remarks. So before I start the talk, so we all are witnessing the machine learning or deep learning algorithm playing a significant role in our daily life. Okay, and to learn a deep learning algorithm, we need a powerful computer and GPUs and extensive data as well. So this is not only in high cost but also damage the privacy of the data as well. The data had to move to a central computer, and the model need to learn. So by doing so, the data privacy is destroyed. So in order to avoid that, recently people have introduced federated learning. So that is a distributed learning algorithm. The data won't leave the device. So the data then will be staying in the device, but the model is learning distributed fashion. That is the federated learning concept. It's a privacy preserving distributed learning algorithm. Okay. So given that introduction, so I'm going to start my talk. As I mentioned, federated learning is an emerging distributed learning algorithm utilizing the computer resources of decentralized device. So it will use everybody, whoever participate in that distributed learning, their GPUs and CPUs are used. Okay, so the user data never leave their device. Okay, hence the preserving their local user privacy. Okay, so different learning tasks can be accomplished, such as image classification or regression or natural language process, etc. But so in the federated learning approach, only one model can be learned at particular time. Okay. So in this talk, I will be talking about averaging based federated learning algorithm, and the key ingredient of our work is to we consider this federated learning in cellular network environment or cellular network environment with the base station is equipped with a massive number of antennas. So this is the 5G base stations are nowadays equipped with massive number of antennas, like 64 antennas or 128 antennas or even more. Yeah, and we will be talking about signal processing techniques, which are mainly used in this massive MIMO system, is zero posing and MMSA pre-coding and combining technique. And we will be considering both IID and non-IID training data sets. Okay, so my background is more on wireless communication and signal processing. So this talk is more concentrate on that part of the topic. Yeah. So you can ask me question anytime as well. So this is the system model that I would like to spend some time. So you can consider this system, this diagram as a single cell cellular network. Okay, so single cell cellular network means we are all like a users. We wanted to communicate. There is a base station somewhere. We communicate through that base station. Okay, so the 5G base stations. This is the 5G base station. This is the equipped with massive number of antennas. These are the users. Okay, these are the users. Okay, each user, these users participate in the federal learning process. Okay, each user have their own CPU and GPU and own data set as well, D1, and they are learning this model. They are learning that model. Okay, so each user, there are end users. Okay, and they all have their own GPU and CPUs, etc., and their own data set. These are the data, and they are learning this model. Okay, so this is the base station, and these are the users. Okay, you can consider this is your mobile phone or your laptop or whatever. Okay, so this is the timing diagram. Okay, so each user at times 0 started to learn the model using stochastic gradient algorithm. The model can be a machine learning technique. Model can be a classification technique or any neural networks. Okay, so using the data, their own data, the model is learned here. So the time t is equal to 0, they started doing the iteration. At time S1, what they do is the model waits at that particular time is transmitted to the base station. This is, I'm saying base station, it can, you can consider this is as a server, okay? That's a server, central server, okay? So it is, so the model at time up to S1 is transmitted to the base station or the server. This communication in wireless communication we call uplink communication. Okay, the user to the base station.
So are these weights disjoint sets, or does each node operate on the entire set of weight parameters?
Sorry, I didn't get to it.
Are the weights, so you have sets of weights that are labeled differently by superscript.
Yeah.
Are those disjoint sets?
Disjoint, yeah, disjoint. Okay. Disjoint sets, yes. So each user have an independent data as well. We consider in the simulation the data can be IID data, or it can be a non-IID data as well. So yeah, these are different data.
No, I think what he means is the data is disjoint.
Yeah.
Will be separate.
Yeah.
But the weighting are the same. I mean, they are trending on the same weighting.
No, at the end we approach the same weight, but initially some weight are different. Yeah.
So there's something in the base station that combines
weight change. Yeah. That's what I'm going to tell you. Okay. Yeah. So each user will learn the weight up to S1 time S1, and then these deep learning models, real parameters. But in communication, we do everything in complex domain. So at this stage, at S1, so the model weight will be quantized and mapped to complex symbols, constellations, and then it will do some pre-coding at these antennas, and it will send to the base station. By doing so, this coordination, etc., there will be some error will be introduced as well. So then it will be sent to the base station. This is all wireless channel. So wireless channel also introduce errors due to interference and fading, all these users will sending their model weights at the same time at the same frequency, so they all interfere as well. So there is a communication errors as well happening in the uplink, and then the base station is receiving all these user weight parameters and then demodulate this weight and then change it from complex symbol to real weight, and then dequantize, etc. And the base station will then aggregate. It can be weighted average of all these user weight, and then this weighted average weight will be broadcast to each user back. Okay, so this weighted average weight will be again pre-coded. This is massive MIMO pre-coders that we will be discussing, and broadcast to each of the users. And this is the red arrow is the uplink. The blue arrow is called downlink communication from base station to the users, and then user will get a weight, and then they keep doing the iteration until the model is converged. Okay. So, so here is the local. This is the local training at T0 to TS1, and then uplink communication is red, and the downlink communication after model averaging, and then again local training, uplink. Okay, so this will continue until the model convert. Okay, any question? Yeah. Okay, so. Let me go through a little bit more on the model as well. So K users store a local training data set, curly DK here. These are the data points. The size of the data set is DK. And each data point is stored input-output parameters, X and Y. X is the input to the model, and Y denote the corresponding output. Okay. The total size of the data is D, capital D is there are end users from summation of 1 to n. Okay. FWD denote the loss function. In the neural network literature, we use sum of square error or cross entropy loss function. So these are one of them. So this is the loss function and the model output based on W. Okay, so the loss function is defined by this equation here. For the kth user, for the older user, loss function is given here. So it can be written as a weighted sum of the individual user loss function. Okay, so the objective of the learning is to find the W that minimize the FW, this capital FW. So that's the objective. Distribution fashion. Okay, so this is the timing diagram again that I already explained. This curly T is the communication round. So these are the communication round. So these are the instant the local update is happening. So it will take away that communication round as well. So this local training can be we can fix the same number of local training, or we can also vary the local training. At the beginning, we do many local iteration, but at the end, when the model is converging, we can reduce the local training as well. Because we wanted to come up with a communication efficient design. We wanted to save energy and a number of communication round, etc. Okay. So the kth user stochastic gradient step is given here. This is the gradient of that loss function. This is the weight. This is the mini batch. So this shy k denote the mini batch. The k user may not use all the data, training data, so they can use the mini batch as well. Okay, so I guess I mentioned everything here. So the next few slides is something related to wireless communication. Again, so anyway, so this is the system model for uplink. So the users are sending the weight to the base station. So the base station is receiving this Y is the base station is receiving the signal. This is their end user, so it's summation of 1 to n. This is the W is the weight is we put all the weight in such a way in a matrix form, and this is the H is the channel between the users to the base station wireless channels, that is normally relay feeding channel, and this is the uplink power. The user may have an ND number of antennas. That is the additive Gaussian noise. Okay, so at the uplink at the base station, it will do zero forcing combining techniques. This is one of the receiver techniques that MIMO or MIMO base station normally do. So then the base station estimating the weight here. Okay, the estimated weight is true weight and plus the estimation error. Okay, so my next 4 or 5 slides, my objective is to find this weight error variance due to coordination, due to uplink and communication, due to error due to fading and interference, etc. So my objective is to try to find error variant because I wanted my objective here. The story is to do a convergence analysis and come up with a communication efficient design. So to do the convergence analysis, I need some mathematical stuff. Okay. So anyway, so I'm going to find the error variant now. Okay.
So what's the relationship between H of T and H of TK?
So H of T is all the user altogether. Okay.
And why WT is also the stack up of
all the way, all user weight. Yes. So yeah, only next 4 or 5 slides are mathematical. Then we will go back to less mathematical stuff. Okay. Anyway, so here, these are the, as I said, this guy is this is the weight, estimated weight at the base station or server. It's a true weight and plus error. Okay, so I wanted to find the error variant here. Okay, so that's my objective. And here the other parameters are P, U, L mean uplink power, and ND is the number of transmitter of the user. Okay. So this is the matrix. Okay, this guy is a matrix. Okay, so the HT is the concatenated of each of the user channel from the user to base station, and W is the each user weight. So the W, this big matrix cap all the user weight. Okay, okay. So this guy. So this is the matrix, the error, as I said, the column of that matrix is going, we can show is this column of the matrix, covariant matrix is given by this expression here. So each column of the estimation error term has a zero mean. Covariant matrix we can prove is going to be like this. Okay. Now, while we used MIMO, we use MIMO. So owing to the MIMO concept, the base station have a massive number of antennas. Mean this channel matrix, this guy is approaching tends to be identity matrix. Okay, this is called channel hardening effect in by the terminology. Okay, so this is approaching identity. So this guy is become identity. So this covariant matrix is going to be like this. Okay, then we can undo all these all user weight as the k user weight, like we can write it like this. So this is the k user weight at the base station. It's the true weight and plus estimation error. This estimation error have a distribution is distributed as a normal, zero mean, and this is the covariant. So my objective is to find this variant here. The thing here in front of the identity matrix is the variant.
So for those of us who don't know much about the communication part of it, can you give a sort of a qualitative description of the error? I assume that's channel hardening basically reduces interference between the channels.
Yeah.
So you have these channels, and they don't interfere, but each one has a finite error rate due to
due to the multi-path fading. So the when you
Multi-path. So
fade,
part of it is transmission, is part of it also quantization of the weight.
yeah, wait, but the quantization also introduced error as well, but this error happening due to fading and interference. Okay, and the noise as well. Okay, yeah. So this is one. I wanted to get this guy, the variant here. Okay, the two comes from because we convert the wireless communication. In neural network, the weights are real, but we need to do transmission. We need we change this real weight to complex and etc. So because of that, these two come. Anyway, so. Okay, so at the base station, it is taking a weighted average of each user weight. Doing so, it is and also do some quantization as well at the base station, and that is introducing further error as well. So the weight is this is the error. That error we can prove. All these proofs are in the paper that I mentioned in the first slide. Okay, so that is distributed as that this guy is distributed error is distributed as zero mean, and the variant is given here. Okay, so one more slide. So after that is fine. Okay, so now the communication is happening. The base station is going to aggregate the weight and then again do the quantization, etc., and transmit to the users by doing. So again, it is normally do a pre-coding techniques. The 5G base station normally do a pre-coding technique. Anyway, to say everything short, and the downlink weight again have a error. That guy is distributed as normal zero mean, and the variant is given by here. So the total error variance due to uplink, downlink, quantization, etc. It is due to all of these things: up, downlink, averaging at the base station, and the uplink. All these things, the weight is having a these are the error, and this is the true weight. And this guy again, the error is distributed as normal, zero mean, and variant. I will tell you later. Okay. So I wanted to find this variant. Then only I can analyze the convergence analysis mathematically. Okay. So now. To do the convergence analysis, we assume the following four assumptions. These four assumptions are, if you studied any convex optimization techniques, you know all these, you come across all these things as well. So the first assumption is called smoothness. So this is, let's say this is the F1 to Fn are the loss functions at the end each of the user. So they are called L smooth if they satisfy this inequality for given two weight. Okay, the L is coming here. This is the gradient of that loss function. So this is called L smoothness, and these loss functions are mu convex, strongly convex if that satisfy this inequality. Again, the mu is here. This is the gradient again. Okay. The third assumption is a bounded variant for the stochastic gradient. So the variance of the stochastic gradient satisfies this inequality as well. And this is again a uniformly bounded gradient as well. So with this assumption, we can prove that the modal weight is bounded by this each of these iterations. The modal weight is bounded, so the modal weight is reducing. It is not exploiting. Okay, and this is the guy that we derive. And this is the error variance due to quantization, uplink communication, and downlink communication. So this is the variant is have this closed form solution here, and you can see here there are a few things you can notice from this one. So this PDL mean power at the downlink divided by the sigma squared. If you take the sigma squared, the downlink SNR, that is the downlink SNR, which is the critical thing. When you send the base station sending the weight to the users, if you make an error, the conversion will be degraded. So that is one thing that we can observe from this variant analytical equation. Okay. Anyway, so the message here is the way the weight will be when you every iteration the weight will be decreasing. The error will be decreasing, not the weight. The error will be decreasing. It's not exploding. This is another lemma as well. I will skip here. This is the conversion analysis theorem. This is the main theorem of that paper. The cost function will be converged, and it is converging in the order of t minus 1 and sigma squared. T minus 1 means the time. So if we do more round, it is it is converging as well with respect to t to the inverse. And if the sigma variant is small, error variant is small, it will also converge fast as well. So that is the measure. So the Federated algorithm reduce in the order of t minus 1 sigma squared manner. Okay. Anyway, so that's all the mathematics. So another thing I would like to tell you before showing the simulation results, the overall communication cost is depends on number of round that we are number of communication round and number of model parameters and the normalized transmit power and the number of quantization bits. So if you have a larger quantization, then the cost of the communication is increased. If you have larger model parameters, the communication cost increase. If you do more communication rounds, the cost will be increased. So we will like to come up with some efficient Federated learning algorithm as well. So this is the proposed Federated learning algorithm, which is we call communication efficient Federated learning. Initialization, the R is going from 1 to T. This is the number of round that we do this learning. Here is the downlink transmission. We also not transmitting constant power over the time. We varying the power because we wanted to do a communication efficient design. So we vary the downlink power according to this formula. This means we transmit less power at the beginning, but when the learning algorithm is converging, we do transmit a high power. So this is the formula power budget formula here. Why we wanted to do that is when things are converging, we don't want to make any error. So that's the way. And initially we do a less power, but when the learning is converging, we do high power. Similarly, this is for downlink and similarly for uplink as well. So this part of the algorithm is for the downlink, and this part of the algorithm is the averaging effect. Okay, and this part of the algorithm is a local iteration at the user side, and we also because we want to do a communication efficient design, there is a user selection. So we start with, let's say, 15 users. During the process, we can also only select few users, not everybody. So how do we choose the users? One way to choose is to choose the users who have a good channel quality from the base station. So choose the best channel quality users. Or other choice is to choose the users their weights are far away from the ideal. So if the L2 norm is bigger, then we choose those users to participate further learning. So yeah, so let me summarize. This part is the downlink part. This is the kind of averaging at the base station part. This is the user selection part, and this is the local iteration each user site, and this is the uplink part. Yeah, that's it. So this is the full algorithm. Okay, so I'm going to show you extensive simulation results. So we used 3 data set. The first data set, MS data set. This is the, this is the handwritten data set from 0 to 9. So there are 10 classes to classify. And then extended MS, this is the handwritten English letter from A to Z. So there are 26 classes to classify here, and the fashion MS, there are 10 float. So again, this guy and this guy only 10 classes, and this guy data set have 26 classes. So these we use all 3 data sets. We use 25 users participate in this learning, and this is the model, CNN model used here. The base station we consider 64 and now 128 antennas. Yeah.
So in total, how many parameters you need to train?
Train so
15 layers. And
15 layers. Per layer. It will come in the simulation. Okay. So the global round is 100 global round, CSI known at the base station, relay fading channel. Yeah, we use 2 quantization. One is called uniform quantization, other one is called stochastic round based quantization. We use QPSK modulation. Yeah, so the learning rate need to also change during the learning as well. This is the uplink power budget, and this is the downlink power allocation budget as well. Okay, so these are the kind of SNR uplink power over sigma square noise power, and this is the downlink SNR. So this is the first results. This is the testing accuracy at the local user side. Okay, so this is the testing accuracy of the at the local user side. This is a global communication round versus at downlink SNR is fixed at 10 dB, but for these different curves for different uplink SNR. Okay, so so repeat again. This is testing accuracy versus global round, and the green curve is the baseline. Here, there's no error. There's no quantization error, no communication error, or nothing. So it's all perfect. So if we approach green, so we are doing well. Okay, so you can see at uplink SNR at -3 dB, this magenta color is almost achieving the green. Okay, so so we can see from here. So what is the SNR is required to achieve the perfect case. Okay, so that's why this is different curves are for different from SNR. So this is the magenta was -3 dB, and this guy is -8 dB. Okay, the green is the baseline, meaning there's no error in this error. Okay, perfect case. So this is the testing accuracy at the user side, and this is the testing accuracy local user side. This is the server side actually. Okay, this is the testing accuracy at the server side. Again, okay, so this is again testing accuracy at the local user side, but we are changing the downlink SNR, but we fixed the uplink SNR to -3 dB. So in the previous case, the -3 dB uplink is good enough. So we fixed that here. We fixed the uplink to -3 dB. And then we check what is the downlink SNR is required. Again, the green one is the perfect case, the baseline, and you can see at 10 dB downlink SNR, it is approaching the perfect case. Okay, so by doing these two simulation results, we are finding what is the SNR required for the to achieve the perfect case. So this is the accuracy at the local user side, and this is the similar curve we can get for the server side as well. It's not as given in the slide. It is in the paper. Here is the testing accuracy versus uplink SNR. Okay, for different curves are for different downlink SNR. So here again, the green one is the perfect case. And there is other literature. People also studied this kind of scenarios, and one of the literature paper they consider downlink from server to the user. They consider perfect. There's no error. So because the downlink from the server to the user link is the main challenge. If that link have a cause error in the communication, the federated learning algorithm convergence will be an issue. So people notice that, and some people analyze the algorithm, assuming the downlink from server to user is perfect. So that is the plot. Is the black plot. The downlink is error-free. Okay, downlink is error-free. But we consider both uplink and downlink is error cases, and you can see the black curve is the downlink is error-free. But the light blue here at the downlink at 10 dB, it is almost same as the error-free case as well. So that is the observation here. And the previous plot we saw, the uplink is -3 dB is good enough as well. And again, the downlink is 10 dB to get acceptable result. Okay, so as I said, there are two signal processing techniques, linear receivers and precoders used in the 5G system. One is called zero forcing, other one is called MMSE. So here is the testing accuracy versus global communication ground for the two receivers and precoders. And we know the MMSE is performing better than the zero forcing, so that is also observed here as well. But the analytical proven if we only use zero forcing, because MMSE, if we use MMSE precoders and combiner, the analytical proof is not easy to get a closed form solution. So we use only zero forcing for all the results, the numerical results that I showed before. Anyway, so the conclusion here is the MMSE is receivers and precoders performing better compared to zero forcing. So okay, and this plot is testing accuracy versus communication round again. This is a full, every user is participating in the learning, and there are three user selection. Everybody is participated, and best 10 users participated, and L2 norm-based selection that I mentioned is participated as well. That is the blue curve. Uplink channel state-based selection, the best users are selected, 10 best users are selected. Those results are in the red. So you can see if you have more users, of course, the performance is better. But if you wanted communication efficient design, then we can select a few users in the level. Okay, so this plot is again testing accuracy versus communication round here. The blue one is the fixed SNR. So we always transmit fixed SNR. And the black curve is we are changing the power of the transmit power because we wanted to come up with a communication efficient design. So we changed we started with the less power and increase the power as the learning goes. That is the black curve. So you can see it is a performance degraded, but in terms of cost, it is less compared to this guy. Okay, so that is these two curve, and here here is the testing accuracy. This is the loss function. This is the loss function. So this is again the red one is the fixed SNR, and magenta one is the varying SNR as well. The green one is our convergent analysis, the theoretical results. As you can see, the green one is matching with the simulation as well. So the green one is the mathematically proved the convergent curve. Okay, so the message here is if you vary the power, we will get less cost learning, but the performance bit, we will be sacrificing a little bit of performance as well. Okay, so here this table is showing different quantization. So this is for the 10-bit quantization. This column is for 12-bit quantization, and this column for 14-bit quantization, and the 16-bit quantization. Okay, so again, these are the accuracy. So as you can see, if you increase the bits for more bits for quantization, the accuracy is increasing. This is the IAD data set. And here again, varying the SR, the number of local training is fixed, varying SR, but fixed power or varying power and fixed power, or fixed SR, local training is fixed, varying power and fixed power, etc. So the conclusion is the fixed power is normally performing better. And also, if you have a more quantization bit, things are performing better as well. So here, we didn't see much differences, but here this is the non-IID training data set. Non-IID data set mean in the data set, some of the let's say if it is MNS data set, some of the letters are more occurring than the others. Okay, so again, this is the different quantization bits. You can see here, fixed power with the varying local step iteration is performing better compared to all others, and here again, if you go from larger bits, quantization bit, its performance is also increasing as well. So this is the testing accuracy results versus again global communication round. Here is the different non-IID NAS. Okay, so the green one is the perfect IID case, and if you have a non-IID NAS, the performance is degrading. This is the 90% non-IID-ness is the black one. The red one is 40% non-IID-ness. Okay, so if you have a non-IID data set, the performance accuracy is degrading as well.
So how does factor is defined? How does factor is defined? The non-IID factor.
Okay, so some of the letters, as I said, occur more. If it is if it is a MNS data set, there are 10 classes. The classes are all kind of equally likely.
Yes.
Non-IID, some of the classes will be more occurring.
Yes.
Yeah.
But then how we arrive to that factor? So like 40 or 50%.
50%. So the 5 of the letters is always occurring more than the other 5 or something like that.
Yeah, it must be.
Okay, so here, this is again the testing accuracy global communication round for different quantization here. So this guy, this is a 16-bit, the solid kind of a magenta, it's a 16-bit uniform quantization. and the dotted line for same color is a 16-bit quantization. The blue ones are the stochastic round quantization as well. The stochastic round quantization use only 8 bits. The non-uniform, uniform quantization uses 16 bits. So, of course, the stochastic rounded is, less coarse compared to the uniform. But again, if you consider this is a 8-bit using stochastic rounded quantization. This is a uniform quantization with a 16-bit. So obviously the stochastic rounded quantization is a better choice. Okay, so here is the testing accuracy again with the global communication round for three different data set here. So this is the MNest data set. And this is the again the fashion MNest data set. These both are classifying 10 classes, and this guy is for extended MNest. There are 26 classes to classify. So this is the extended MNest data set. So again, this is even though there are these two set are the 10 classes, but these classes are very close together, so that's why its accuracy is less in the case of fashion MNest. Okay, so that's all I would like to say. So in this talk, we have analyzed the parallel learning in the multi-user massive MIMO cellular network. We consider imperfection at the uplink and downlink link. We use zero forcing and MMSE scheme for uplink and downlink precoding and combiners. We derive the type convergent bound in this order here. And we come up with some communication efficient design in terms of varying the power and varying the local training steps, etc. And we use different data sets. The power convergent bound is in the order of T-1 and sigma z squared. This is the total variance. Okay, so all these equation and proof are given in this paper if you are interested, and that's all I would like to say. Thank you for listening. Yeah.
So I have a couple of questions. One, I might have missed it, but it seems like the number of iterations that are performed on the independent nodes between the communications rounds must have some effect on it.
Yeah. So that's what that is called SR.
So I probably just missed the definition.
Yeah. So yeah. If you go to the first slide. Here, yeah. So this is the SR. In between there are we call, let's say, SR. So we make this is the same for all the R's, or we change when the communication going. So the learning goes. We reduce the learning from local training. Initially start with more local iteration and varying the reducing the iteration once the weights are converging. That is a good thing to do if you want less communication cost. So your question is
well, my question is basically how many iterations are carried out locally between communications routes?
Yeah.
I mean, so you said, well, we decreased that.
Yeah.
From, is it
50, let's say 50 at the beginning, maybe we used to have 5 or 10.
I'm just curious what the order of magnitude.
Yeah.
Because you could wander very far from a global optimum weight set if you let it iterate too long, right?
Yeah.
Okay, second question is, would you gain anything? Could you reduce the required quantization accuracy if on the uplinks you transmitted weight update values rather than weight values themselves?
So from uplink?
I mean, you know, you're iterating, you're computing changes in the weights, right? So at the end of that, you have some accumulated changes, and you could transmit that in the uplink rather than the full weight value. Do you think it would be possible to do that at a lower quantization level or quantization resolution than transmitting the weights themselves?
Okay,
Does that make sense?
Let's say the weight is I don't know, weight plus delta. Okay, the true weight is something plus delta. So you are saying only send the delta?
Right, send the delta, or send the accumulated deltas over.
Oh, yeah, okay, yeah. Yeah, we can try to see those kind of, if we can reduce the communication bits, it's going to be efficient. Yeah, that's
Right,
one.
I'm just guessing that maybe you could reduce the number of bits
But, yeah,
if you transmitted the delta. instead.
Yeah.
So,
okay, any other question?
So I have a question. So for the federated learning, anybody look at from the perspective of statistical learning? Points of view, because to me, it's like this. Okay. You are going to do, let's say you have a whole data set, right?
Yeah.
And you want to get the distribution for the weight, right? So you got this. Okay. Now, if you have this individual data sets, you let's say at the user I, what you try to do is this. This. Okay. So let's say that you try to find the distribution of the weight at user I, right? And then instead of you send the weighting factor as the point estimate, you send the distribution of the weight.
Okay.
To the central users, to the base station. Okay? Then the base station would try to find a way to re-estimate this thing because they have different versions of it. Right? So let's assume that you use.
Okay, so basically you're saying instead of sending the weight, but send the distribution. Okay.
Let's say try to want to combine all these things together in some rule. Okay? Let's say it's a function of this thing. Okay. So, right. Then when I have this, I send this one back into the user. And this thing we use as the new prior for the next update.
Okay. I haven't seen this kind of work. Yeah.
Okay. Good.
So you can do that.
I can always come here. Because it's basically when you try to learn the weighting factors, you know a network to calculate in that sense, right? So, but if you use forget if we don't have the neural network, we just use a more standard learning method. Because you do in what's the distribution of, because the optimal one is you have a full data set, right? You're trying to get the weighting using the full data set.
Yeah.
Or you get the weighting factors
From the each
versions.
version,
Using only the local data set.
Yeah, okay.
And then you fuse individual distribution into the.
Yeah.
Okay. Yeah, okay.
Yeah. But there are work, we call this is the privacy preserving learning. Okay, the data are not learning, leave all the data are sitting in the user device. But there are papers, if you send the weight of the model, the Eve can get the data information, etc. So there are some attack papers on this as well. Yeah. And then people now working on putting some, security aspect.
You're talking about inferring something about a user from the model that results, global model.
Sorry?
I'm trying to understand what you're saying. Are you saying that use the word attack, right?
Yeah. No. Yeah. So some Anyway, so it's okay. There are security issues. We say it's a privacy preserving learning, but there are a way the data can be leaked with the model. From the model, the data can leak as well. Yeah.
So you can infer something about the data.
The data from the weight. So there are papers on that. I think this is still active research, and yeah, there are some funding call I recently see on federal learning, the title is federal learning. Anyway, so my background is wireless communication signal processing. So we, mapped the federal learning to our domain and did work here. Yeah.
Is there any other question? All right, so, all right, thank you. Yeah. So, it's okay. When you do the estimation of the.
We were on witnesses of 500.